Today in section 12.1, we'll look at the first derivative. Now, notice that we have to call this thing now the first derivative because, in fact, you could start taking derivatives of derivatives. If you take the derivative of a derivative, that's going to be, or at least the derivative of the first derivative will be the second derivative, the derivative of the second derivative will be the third derivative, etc. And so everything that we've done so far in this class has been the first derivative. And so we now have to be a little more specific. Here is the function that I was just playing with in the GeoGebra, x cubed minus 3x. And the question is, where does f have horizontal tangent lines? You told me that it has horizontal tangent lines when x is equal to a negative 1 and where x is equal to positive 1. And then how do we describe the graph at these turning points? They're sort of turning points for the graph, so maybe we could say that. The technical words we're going to use will be local minimum and local maximum. So here's a local minimum. It's the smallest y values in the graph in that little neighborhood. Okay? So certainly there are smaller y values on the left side of the graph, but in this little piece of the graph, that is the smallest because it dips down and comes back up. Similarly, here is the local max. That is the largest value for the y function, the y values, in that little range. Okay? All right. Consider the first derivative of f. The derivative of f gives us the blank of the graph of f at each point. What does it give us? What is the slope? What is the derivative measure? The derivative measures slope. All right. If f prime is greater than 0, that means it's positive. That means we have a positive slope. Then the graph is what at that point? Increasing. If the first derivative is negative at some point, then the graph is decreasing at that point. And if the first derivative is 0 at some point, then the graph has a horizontal tangent line. At that point. All right, let's use that same function. F of x is equal to x cubed minus 3x to find the first derivative. Create the sign chart for the derivative to find where the derivative is positive, negative, and 0, and then state where f is increasing and decreasing. So we can do this. We can do the sign chart either in the box form, like it has printed here, or we can do it the original way that we learned last week. So let's start with the function. F of x is equal to x cubed minus 3x. Take the derivative. This will be 3x squared minus 3. We want to know where the derivative is positive and negative. To do that, we remember this idea that we had last week, that a continuous function, like this polynomial, can only change from being positive to negative if it goes through 0. Right? There's no jumping because it's continuous. So that's why we set it equal to 0 to find these partition points, where it could split up. Factor out the 3 from 3x squared minus 3. That gives me 3 times x squared minus 1. Factor x squared minus 1. And to no surprise, that gives me x equals 1 and x equals negative 1, just as we stated previously. Remember, the 3 doesn't count because that would be 3 equals 0, which has no solution. Now we could go ahead and make the sign chart on the number line like we've done before. Here's the x, and then here's the f of x. Actually, not f of x, f prime of x, rather. And so the 2 points we need to mark are -1 and +1. We're measuring the first derivative, and the first derivative is 0 at both -1 and +1. And then we need to test these intervals. We need to test what happens between -infinity and -1. We need to test what happens between -1 and 1. And we need to test what happens between 1 and 0. Y'all should probably be taking notes over this. Okay. So I'm going to test at -2. So we have 3 times -2 squared minus 3. That should be 9, which is positive. So we have positive all in this area. Then test between -1 and 1. That's f prime of 0. Oops. That would be 3 times 0 squared minus 3, which is -3. That's negative. And then we need to test a number between 1 and infinity. We'll test it too. So this is 3 times 2 squared minus 3, which is +9. And that's positive. And we get positives. Now the interpretation that we need is what the sign of the derivative is. How does that correspond to what the function is doing? When the derivative is positive, the function is doing what? Look on your chart. It's increasing. When the derivative is negative, what is the function doing? It's decreasing. So that's what you will tell me. F is increasing on, and then you pick up the intervals where the first derivative is positive. So that is -infinity to -1, union 1 to infinity. And then f is decreasing on -1 to 1. Because from -1 to 1, that's where the first derivative is negative. Alright, so that's the big idea for today. You look at the derivative's sign to determine what the function is doing. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. We use things that we did in the past to find where these intervals occur based on sign charts and finding partition points, where it's 0 and where it's undefined, etc. Questions? All right, let's look at example 3. I'll let you work that one with your partner. Example 3, f of x is equal to 4x minus x to the 4th. So we'll take the derivative. Set that equal to 0. We get 4 times 1 minus x cubed. So we can factor this one using the difference of cubes. It's 1 minus x is 1 plus x squared equals 0. Set the 4 equal to 0, you get nothing. Set 1 minus x equal to 0, you get x equals 1. If you set 1 plus x squared equal to 0, it doesn't factor. You could use the quadratic formula, but you'll get a negative under the square root. So there's no real solutions here either. And we don't use i's, the imaginary roots, in this class. So the only number you get is x equals 1. That's your only partition point. So we get a 1. That's your x's. We're testing the derivative. Now you can use any form of the derivative that you want. There are actually 3 different versions of the derivative in this problem alone. You could go back to this, that was the original derivative. You could use this one, or you could use this one. All 3 of these are the same. The one that I usually use is the one that's factored to the extent where it helps me figure out what the signs are. In this problem, it's this middle one. Okay. So we're going to test points inside each interval. So we're going to test 0. 0 is in the first interval. So that would be 4 times 1 minus 0 cubed, which is positive. I don't even care what the number is. I just know that it's positive because I have a positive number here and a positive number in this factor. So a positive times positive is positive. Next, let's put in 2. So we have 4 times 1 minus 2 cubed. Again, we have a positive for the first part, the 4. What is 1 minus 2 cubed going to be, positive or negative? It's going to be negative, so a positive times a negative is a negative. And so I just put in some negatives. And then what statement can be said about the increasing and decreasingness of this function? F is increasing on, and then what interval is it increasing on? Negative infinity to 1. And then F is decreasing on 1 to infinity. So that is the type of answer we're looking for in today's assignment. Questions over example 3. All right, so that leads us to the definition of critical values. So the critical values of a function f are the values of x in the domain of f where f prime of x is equal to 0 or f prime of x is undefined. We've only seen this first case so far, where the f prime is 0. We will get to problems where the f prime is undefined. That'll also be what we call a critical value. And then these critical values lead us to the partition points of f prime. And we also have to use points outside of the domain. Right? So use also points outside of domain of f. Actually, I think we should technically say these are partition points of just f. So that way we don't get in trouble with the second derivative. Yeah. Just change this to an f instead of f prime. All right. Example 4, find the critical values of f of x is equal to x to the 5th plus 3x to the 4th minus 3x cubed. So to find the critical values, you need to find where the derivative is equal to 0 or the derivative is undefined. All right, so we set this, find the derivative, then what type of function is this? Polynomial. Polynomials are continuous. Where? Everywhere. So the first part of, the second part of the critical value definition. Where is f prime undefined? It is not undefined anywhere, so that part is taken care of. So the only part you need to worry about is the f prime is equal to 0. So set it equal to 0, and then factor 5x to the fourth plus 12x cubed minus 9x to the fourth. I see I can take out x squared. So we have x squared times 5x squared plus 12x minus 9 equal to 0. We have 5x and x, because 5 is prime, so it has to be 5x if it's going to work at all. And then what are the factors of 9? We got 1 and 9 and 3 and 3. Let's try 3 and 3. 5x times 3 is 15. 3 times x is 3x, so 15 minus 3 is 12. So that's going to work. We need the 12 to be positive, so I need a positive on the 15. So 15 is positive, 3x is negative. Now, take each factor and set it equal to 0. So x squared equals 0, 5x minus 3 equals 0, and x plus 3 equals 0. So we get x equals 0, x is equal to 3/5, and x equals negative 3. And those are your critical values. So where do your critical values come from? Two places. F prime is 0 or f prime is undefined. Let's take a look at example 5.
What's the difference between the critical values and what we did in example 3?
Not much really. In example 3, x equals 1 was the critical value. Okay, but what you can have is you're going to have to form the line, the number line, so that you can do the sign chart. The critical values will go on the line, but you may have to put in other values. The other values will be points where f is discontinuous. So yeah. All right, example 5. Find the critical values for f of x is equal to the square root of x. The first thing we need to know about this one is what is the domain? What is the domain of the square root function? It is 0 to infinity. All right. F prime of x is equal to what? Or 2 squares of x. And so we need to find the critical values. The critical values occur when the derivative is equal to 0 or when the derivative is undefined. These are our two ways to get critical values. To solve when a fraction is equal to 0. So in other words, this would be 1 over 2 squares of x equal to 0. To solve when a fraction is equal to 0, that is the same thing as setting the numerator equal to 0. 1 equals 0 is not true. So there's no solution from that piece. Next, we look at f prime is undefined. So 1 over 2 squares of x is undefined when the denominator is equal to 0. So solving that for x, we would get, first you divide by 2, and then square both sides, and you get x equals 0. Now before we declare that this is a critical value, you have to check the domain of the original function. One of the conditions for being a critical value is it's a value in the domain of the original function that is then undefined in this half, right? Undefined in the derivative. Is x equals 0 a value in the domain of the original function? It is, because it's closed at 0, so this is in fact a critical value. You can have functions that are undefined at a certain point, and then you take the derivative, then you still get that value as a critical value. Well, you get it whenever you set it and find where it's undefined. But because it was undefined to begin with, it doesn't count as a critical value. You still use it as a partition point, but it's technically not a critical value. Next, we talk about the local extrema. So, first off, the local extrema refers to the local minimum or local maximum local extrema occur only at critical values. But not all critical values result in local extrema. So recall that the local extrema, the local min and the local max, those are the points on the graph where the graph turns around. It goes from increasing to decreasing or from decreasing to increasing. If you're going to have a local extreme, you have to have a critical value associated with it. But just because you have a critical value does not necessarily mean you're going to have a extreme value. And we saw this when I was working with the graphs yesterday. We'll go ahead and show it explicitly in example 6. Show that f of x equals x cubed has a critical value, but no extrema. So, what is the derivative of x cubed? 3x squared. 3x squared is a polynomial, therefore it's continuous everywhere, therefore it is never undefined. The only critical values this function could have is when it's equal to 0. So set it equal to 0 and solve for x. And so you get x is equal to 0. X equals 0 is the critical value. Next, let's draw the sign chart. The only critical value on the sign chart is 0, and that's when the derivative is 0. If this function has a minimum or a maximum, then the graph has to either be increasing followed by decreasing or decreasing followed by increasing, which means that one half has to be positive if we're looking at f prime, the other half has to be negative, or vice versa. What are the signs that go in the first interval and the sign that goes in the second interval? You can use this version of the derivative to find those signs. Notice that 3x squared is always what? It's always positive. X squared is always positive. So you could test some points, but since you know that x squared is always positive, and then multiplying that by positive 3 is always positive, we know that this derivative is always positive except at the critical value x equals 0. That tells me that the graph itself is increasing followed by more increasing, which is no extreme value. Questions over the theorem here. The theorem again states that if you have an extreme value, it must occur at a critical value, but just because you have a critical value does not always result in an extreme value. All right, let's do example 7. We want to find all extrema of f of x is equal to x cubed minus 9x squared plus 24x minus 14. What do I need to find in order to find the extrema? You find the derivative in order to find what? Where do all extrema occur? At the critical values. So we need to find the critical values. In order to find the critical values, we need to find f prime, and then we will find where f prime is equal to 0 or f prime is undefined. All right. F prime of x is equal to 3x squared minus 18x plus 24. That's a polynomial, so it will never be undefined. Set it equal to 0. Factor out a 3. So we get x squared minus 6x plus 8. How do you factor x squared minus 6x plus 8?
X minus 2, x minus 4.
Very good. X minus 2, x minus 4. Set each factor equal to 0. So we get 3 equals 0, x minus 2 equals 0, x minus 4 equals 0. No solutions from the 3 equals 0 part. X is equal to 2, and x is equal to 4. We now have the critical values. We need to determine explicitly which critical values we have. What are they? Are they local mins? Are they local maxes? We'll do that by creating the sign chart. So we have f prime, and we have x. We need to test the derivative to see if we have a positive or a negative. And I'm going to use this version of the derivative. So we have f prime of 1. No, actually, I'm going to use 0. 0 is the easier number to use. F prime of 0, so it's 3 times 0 minus 2, 0 minus 4. That would be a positive times a negative, which is a positive. So we're positive in this first interval. I'm going to test the derivative at 3 for the middle interval. So we have 3 times 3 minus 2 times 3 minus 4. That's a positive, and a negative, which is a negative. And then we will test it at 5. 3 times 5 minus 2 times 5 minus 4. That is a positive times a positive times a positive. That is a positive. Now, where is the graph of f increasing? So here's f increasing, and then here's f increasing because the derivative is positive. Sometimes you'll see people write INC. Sometimes you'll see people write this increasing arrow. It's not straight up and down. We use straight up and down for concavity, which we do later on today. But it's a slanted one. And then it's decreasing from 2 to 4. You'll also see this decreasing arrow here. Now, if we know where the function is increasing and then decreasing, we can find the extrema. A maximum comes from increasing followed by decreasing. So where do we have a local maximum? X equals 2. So we have local max. Let's find that. So f of 2. Now, notice I put f of 2. That is the original function value. So you have to take 2 and plug it into the original f. And that is a 6. So we have a local maximum at 2 of 6. So the value of the local maximum is 6. What about a local minimum? A local minimum would be where the graph is decreasing followed by increasing. Do we have a local minimum? We have a local minimum at x equals 4 because the graph was decreasing followed by increasing. Let's compute the value of the local minimum. And I get f of x is equal to 2. On page 4, we want to do example 8. Find all extrema of f of x is equal to x minus 1 raised to the 4/5 power plus 3. So again, in order to find the extrema, we need the critical values. To find the critical values, we need the derivative. To do the derivative, we'll use the power rule along with the chain rule. So we have x minus 1 raised to the 4/5. Use the power rule, bring the 4/5 to the front. The inside stays the same. Decrease the power by 1. So 4/5 minus 1 is negative 1/5. Now, the inside was not just the x. It was something else other than x. So we need to multiply by the derivative of the inside. What is the derivative of the inside? It's just 1. So it didn't change anything, but you still have to think about it. And finally, what is the derivative of 3? 0. So that is the derivative. You can leave it like that, or probably better to do it this way. Four over 5 times x minus 1 to the 1/5 power. Next, we want to find the critical values. The critical values occur when the derivative is equal to 0 or when the critical value is undefined. So if we want to know when f prime is equal to 0, we have a fraction for f prime. We take the numerator and we set it equal to 0. So we get 4 equals 0, which yields no solutions. The other way to get a critical value is to take the derivative and find where it is undefined. To find where a fraction is undefined, take the denominator and set it equal to 0. To solve this for x, first divide both sides by 5. So we get x minus 1 to the 1/5 is equal to 0. I need to get rid of the 1/5 power. What power could I raise both sides of the equation to get rid of the 1/5 power? Raise it to the 5th power. All right. And the reason that works is because when you raise it to successive powers, you end up multiplying the powers together. You are trying to get a power of 1. Right? X, when you're solving for x, you're really solving for x to the 1st power. Right? So 1/5 times 5 gives me that power. In general, what do you need to raise it to if you were given some power here, not just a 5th, but any power? How do you come up with the number that you raise it to? You take the reciprocal. Yeah, because the numerator could be something else as well, right? It could be like 2/5, and then it would be 5/2. So you raise it to the reciprocal power. That leaves me with x minus 1, 0 to the 5th is 0, so x is equal to 1. That is our only critical value. Let's create the sign chart. So here's x, here's f prime, here's 1. I'm going to use this version of the derivative. So f prime of 0 is 4 over 5 times 0 minus 1 to the 1/5. That would be a plus over a plus times a negative. 0 minus 1 is negative 1. And 1/5 as a power is the 5th root. If you take the 5th root of a negative, that result is still negative. Right? In fact, the odd root, any odd root, cube root, 5th root, 7th root, 9th root, etc., of a negative stays negative. So this is a negative. Now, f prime of 2 would be 4 over 5 times 2 minus 1 to the 1/5. And that's going to be a positive. 4 is positive, 5 is positive, and 2 minus 1 is positive. So everything is positive. So what extreme value do we have? Do we have a local minimum or do we have a local maximum? We have a local minimum because we have decreasing followed by increasing. So we have local min at x equals 1 of, and then we plug in the 1. If you plug in 1, you get 3. 1 minus 1 is 0. 0 to the 4/5 is 0, plus 3 is 3. Example 9, find all extrema of f of x equals 8 natural log of x minus x squared. So we find the derivative. The derivative of 8 natural log of x is 8 over x. The derivative of x squared is 2x. We need to find where this function is equal to 0 and where this function, this derivative, is undefined. So we will set it equal to 0. To solve this, I'm going to move the 2x to the other side. So we get 8x is equal to 2x. Cross multiply. You get 8 is equal to 2x squared. Divide both sides by 2 and then if 4 is equal to x squared, what must the x be? 2 or negative 2. Yeah. So x is equal to 2 or negative 2. Now, one of the rules about critical values is that they have to be in the domain of the original function. So let's look at the original function. 8 natural log of x minus x squared. What is the restricted domain for the natural log function? 0 to infinity. Yeah, open at 0. So that means the x has to be greater than 0, which eliminates which of my quote-unquote critical values. Yeah, negative 2 is out. Again, critical values have to come from the domain of the original function. The restricted domain of the natural log function is 0 to infinity. Negative 2 does not fall within that range, that section, so negative 2 is out. So the 2 was found by setting the derivative equal to 0. What if we look to see where the derivative is undefined? The derivative was 8 over x minus 2x. A function is undefined when its denominator is equal to 0. And so what value of x would make this function undefined? 0. So x is equal to 0. But now what? Nicholas? Is this a critical value? No. Clinton, why not? Yeah. It's not in the domain. Not in domain. So if it's not in the domain, it has to go. Let's create the sign chart. Now you have to be careful. We don't have the full line here, do we? We have this deal. We have 0 as an open endpoint, and we have 2 as the critical value. These are x's, this is f prime. So we need to test a number between 0 and 2. And we need to test a number between 2 and 3. Between 0 and 2, I'm going to pick 1. So 8 over 1 minus 2 times 1 is 8 minus 2 is 6, which is positive. And then f prime of 3 is 8 over 3 minus 2 times 3. 8 thirds minus 6, which is negative. So what type of extrema do we have? We have a maximum, local max. And where on the x-axis is the extremum located? Local max at x equals 2 of, and then we plug in the value. This is going to have to be a decimal because of the natural log function. .545. Now on your homework, the computer may ask you to enter the exact answer. This is an approximation. The exact answer is 8 natural log 2 plus or let's see, minus 4. That's the exact answer. This is just a decimal approximation. So usually on my math lab, it will put it in blue letters below the answer box what it is asking you to write the answer as. It'll say enter or type an exact answer or enter a number rounded to 3 or 4 decimal places. So the first set here is when you have some value of c where the derivative is equal to 0. So that's the c represents a critical value. It's the critical value found when the derivative is equal to 0. And you have these 4 scenarios that can happen. You can have a graph that looks like this, and then here's c, and then the derivative is negative followed by a 0 followed by a positive. If that is the case, then you have a local minimum. Okay. So what the first derivative test is describing is the combinations that can happen based on what the critical value is and based on what the derivative is doing before and after the critical value. Suppose we have a critical value of c, and the derivative before that is positive, 0 at c, and then negative. That would be a local max. Bless you. Suppose we have a first derivative that is positive, then 0 at c, and then positive. So it looks something like this. We have a horizontal tangent line there. This one has no extrema. No extreme. Because it's increasing followed by increasing. And the same thing here. The first derivative here is negative, 0, then negative. That results in no extrema. Now, what happens if we have a critical value at c where the derivative is undefined? So suppose we have negative, undefined, followed by positive at x equals c. That's the cusp here. So the first derivative is negative, meaning we're decreasing down to this point right here, and then we're increasing after that. So that is a local minimum. What if we have positive, then undefined, and then negative? Well, that's the upside down version of the cusp, and that results in a local maximum at that point. Because we have increasing followed by decreasing. Then suppose we have increasing, undefined, and then increasing. Looks like this, where at some point here the tangent line would be vertical, and that is no extreme. And then the same thing. That's not sharp enough. Do it again. So something like this. Negative, undefined, and negative. No extreme. The first derivative test tells us how to use the critical values and the signs of the derivative around the critical values to determine what type of extrema we have, if we have any at all. Questions over the first derivative test? You've been using the first derivative test the whole period. It's just that's the name of it. I just don't like the name. All right. One other skill that we need to develop in this section is the ability to graph a function derivative given the function graph itself. Okay? So you may not know what the function expression is, you just have the graph. You should be able to graph the derivative to some extent. Okay. The first thing that you should be able to find, and we're going to do the left one first here. The first thing you should be able to find is where the derivative is equal to 0. In other words, what are the zeros of the first derivative? So where does this function have a derivative that is equal to 0? Who can tell me one x-coordinate where the derivative would be 0 on this function? -6. Yeah, -6. So I'm going to put it here. Let me draw this one in red. Now, why is x equal -6 a 0 for the derivative? Because here we have a local minimum. This local minimum corresponds to a horizontal tangent line. Horizontal means that the slope is 0, and the slope is measured by the derivative. So the derivative must be 0. Where else does the derivative have a 0? X equals -2, because we have a horizontal tangent line here. And where else? X equals 3. So first thing you should do is mark the zeros. Now, the next question. You have to figure out where the derivative is positive and where the derivative is negative. If the derivative is positive, what does that tell us about the function itself? And if the derivative is negative, what do we know about the function? Decreasing. So here is the function decreasing. So what can you tell me about the derivative? It's negative. Now, we're just doing sketches. We're not getting this exactly right, but we're probably getting it pretty close. Notice that this is pretty steep right here. But it's negative because it's going down. Steep and negative means it's sort of really has a negative value, so somewhere down here. As we move in from left to right, these tangent line slopes get more shallow because they have to approach 0. So that means the value, it's still negative because it's decreasing, but they're getting to be smaller negative or smaller numbers in absolute value. So we're getting closer and closer to this 0. Now, what happens here at -6? The derivative is 0. What happens to the function between -6 and -2? The function is increasing. Increasing results in a derivative that is positive. Right? Increasing function means derivative is positive. Now, so it's going to go up. Now, it can't go up forever because what has to happen? It's got to come back down to where x is equal to -2. And so there it is. From x equals negative 2 to x equals 3, the function is decreasing. Decreasing means that the graph is negative. And then 3 to infinity, the graph is increasing, which means the derivative is positive. So it looks something like that. We don't know exactly what it looks like. If I were to ask you this on a test, I would just expect a very good sketch. Noting where it's 0 and which side of the x-axis these things are on. Okay, so recapping, what did we analyze? We analyzed where the derivative should have zeros based on the horizontal tangent lines. And we analyzed where it should be positive and negative based on whether the graph was increasing or decreasing. Go ahead and do the problem on the right with your partner. All right, you get it? All right, go ahead and check your answers. They're on the last page. So you can actually see what the one on the left should look like as well. So compare and see how close you got. Questions? How'd your graphs come out? Good? Good? Yeah. All right. Any questions over these? All right. Let's take a look at example 11. The revenue function R of x for selling plates is given in the graph. Describe the marginal revenue function R of x. What are the x-intercepts of R of x? So you're given the revenue function. You are asked to describe the marginal revenue function, which is R prime of x. So what do you know about r prime of x? Name one thing that you know about r prime of x. Maybe we could do a little graph of r prime of x. Do it right here. Name one thing you know about r prime of x. R prime of x has a horizontal tangent line? Which graph has the horizontal tangent line? R of x has a horizontal tangent line. Now, what can you tell me based on that? You're on the right track. What can you tell me based on that about r prime of x? It has a 0 at 500. Very good. Yeah. So does everyone see why the statement made was not quite right? The statement was that r prime of x has a horizontal tangent line. We don't know that. What we do know is that r of x has a horizontal tangent line right here. And since it's horizontal, that means the derivative, which is r prime, must be equal to 0. So we have this piece right here. What else do we know?
Domain is
0 to 1,000. 0 to 1,000. What else do we know about r prime of x?
positive 0 to 500.
Yeah.
500 to 1,000.
Yes. So we're going to have a positive graph from 0 to 500 and a negative graph from 500 to 1,000. Let's go ahead and take a leap of faith. What basic graph does this r of x look like? Parabola. If r is a parabola, what is r prime of x? What is it? Yeah, it's just a line. Yeah. If this in fact is some sort of parabola, that's x squared. The derivative of an x squared function must be just an x function, right? So, it's just a straight line. Like so. So what is the x-intercept of r prime? 500. Questions over example 11, Imani?
How do you know where the domain is? How do you get?
Because of the endpoints on the original graph.
Oh,
Yeah. All right, go ahead and do example 12 with your partner. A manufacturer incurs the following cost function to make water ski vest. C of x is equal to 0.05 x squared plus 20x plus 320 for x between 0 and 150. Find the average cost, and this is a daily thing, so find the average cost, and then find the critical values of the average cost, and increasing and decreasing. All right. Go for it. If anyone needs to take a break, this would be an appropriate time to do so. Remember, you have to do the averaging first, then the differentiation. Yeah, actually came from 1319, where the natural log is from 0 to infinity. So the natural log is x. So if you have y equals natural log of x, then that function looks like this. And so the domain is 0 to infinity. Okay? So in general, if you have, say, y equals the natural log of 3x minus 2, the inside of the natural log has to be positive. So you set it positive. So that. So the domain of this function could be 2/3.
Yeah, this right here.
You find the domain of any function, right? Every function has a domain. But if that function involves a natural log, then that's going to restrict your domain. It's just like, you can't take the square root of it. So you got to have a rule for the square root function. Okay, we got it? Let's take a look. So C bar of x is equal to C of x over x. So that should be 0.05x squared plus 20x plus 320 over x. You can reduce this here if you want, or, because you're going to have to take the derivative, you can use the quotient rule later. I choose to reduce it now. Oops. 0.05x plus 20 plus 320 over x. So now we need to know the derivative. So the derivative of 0.05x is 0.05, the derivative of 20 is 0, and the derivative of 320 over x is negative 320 over x squared. There's a trick for doing those. If you want to take the time to learn it, you're welcome to go do that. But it's, a number over x is the number over x squared, and it's negative. So that's it. All right, set that equal to 0. Solve for x. So 0.05 is equal to 320 over x squared. Cross multiply. Divide both sides by 0.05. So we get x squared is equal to 6,400. Okay, think this one through. For this function, if x squared is equal to 6,400, what's x?
80.
What about negative 80?
Doesn't fit into your domain.
It's not in the domain. All right. So the domain was given to you as 0 to 150. So that's where the answers have to come from. So it's this one. All right, let's look at the sign chart. Oops, wrong sign chart. What's our sign chart look like here? It's 0 to 150, period. And there's 80. The function is C bar prime, and then here's the x's. If we test C bar prime at, 10, if you work that out, you get a negative. And C bar prime of 100, you get a positive. So it's negative, 0, positive. That tells me that the average cost is decreasing because the marginal average cost is negative, and that's on the interval from 0 to 80. It tells me that the average cost is increasing from 80 to 150 because the marginal average cost is positive. And the local extreme is actually a local minimum. That is x at x equals 80. And we'd have to plug this in to figure out the value. We're looking for the average cost. Yeah. Yeah, so the average cost at 80 is 28. Yeah, see, that's the interesting thing. As the number of vests increase, the cost is going to increase, right? Because it's costing you more to make these things. The average cost may be decreasing or increasing, depending on where you are in the grand scheme of things. So what this tells me is that average cost is decreasing from 0 to 80, but then the average cost per vest starts going up again after 80. And that is $28 per vest. It's an average cost of your vest. you.